Our next topic in Anatomy and Physiology 1 is still Chapter 2, but a look at biochemistry. So this is Chapter 2, Part B. Biochemistry is the study of the chemical composition of reactions and of living matter, really how they go together. So we have to first look at what are organic substances or compounds and what are inorganic substances and compounds, because they're both equally essential to life. The key definition for inorganic compounds is a compound that does not contain carbon, like water, which is H2O, or salts, like sodium chloride, or even acids and bases, like hydrochloric acid and sodium hydroxide. However, there are some exceptions. An example of an inorganic compound that does contain carbon is carbon monoxide. So a better definition for inorganic compounds is compounds that do not contain carbon in combination with hydrogen, because organic compounds not only contain carbon, but they contain carbon that is bound to hydrogen or in combination with hydrogen. So they'll have covalently bonded hydrogen and carbon atoms. Organic compounds are oftentimes a lot larger than our inorganic compounds, things like carbohydrates and proteins and lipids or fats and nucleic acids. We'll start with the inorganic compounds. One common and very important inorganic compound is water, or H2O. It's not only an important inorganic compound, it's the most important, because 60 to 80% of the volume of our cells is made up of water. And there's some important inorganic compound characteristics that water has, and we're going to go through each of these. But those characteristics that water has as an inorganic compound are high heat capacity, high heat of vaporization, polar solvent properties, reactivity, and cushioning. So let's look at these properties in just a little more detail, and then we'll look at them in just more of a close-up view. So the properties of water, first one, high heat capacity. If you've ever gone to the beach in May, a lot of spring breaks are earlier than they used to be, and you've run into the ocean and it's freezing, even though maybe it's even 90, 95 degrees outside. Well, the reason the water is freezing is because water has to absorb or release a large amount of heat in order to change temperature. So if it hasn't been 90 or 95 degrees outside for very long, then that water hasn't changed any temperature. It's not been able to absorb that heat that's in the outside environment around it in the atmosphere in order to change temperature. And again, that's because water has a high heat capacity. For high heat of vaporization, if you've ever sweated, then you've experienced water's high heat of vaporization and its cooling properties. Because it takes so much heat to be absorbed by water in order for it to change temperatures, it also takes a lot of heat to be absorbed by water in order for it to break bonds. When water absorbs heat, it usually can go from being a liquid to a gas. And breaking those bonds will cause that water to go from being a liquid to a gas. So as you warm up and sweat, which is made up of mostly water, forms on your body, that sweat absorbs your heat, and when it does finally vaporize and evaporate off your body, it takes that heat with it. And that's why sweating is an efficient cooling system, because of that high heat of vaporization of water. Water is oftentimes called the universal solvent, and that's not 100% true. It does dissolve pretty much anything that's polar, because water is also a polar molecule. If you ever heard the phrase, like dissolves like, that's exactly what we're looking at here. Because water is polar, it as a solvent, which is something that does the dissolving, can dissolve other polar substances. This also includes things like ionic substances, such as sodium chloride. And water, therefore, is a great transport medium for the body because many ions and other substances can be transported in these watery aqueous solutions. And then there's reactivity. Not only can things be transported in the watery aqueous solution, reactions can occur in watery environments. Actually, all of the reactions in the human body require what is called an aqueous environment, which just means an environment that has water in it. Hydrolysis and dehydration synthesis reactions are common in the body, and these are going to be reactions that either break bonds via the addition of water or make bonds via the subtraction of water. And then there's cushioning. And we'll talk more about cushioning, especially when we get to the nervous system, because Water is able to protect certain organs from physical trauma, and one of those is the brain. There's a fluid called cerebrospinal fluid, or CSF, that surrounds the brain and most central nervous system structures, and it provides a little bit of buoyancy and cushion in case there were to be any injury to those parts of the body. The next inorganic compound we're going to look at is salts. And salts contain cations and anions. So they contain a positive ion and a negative ion. They, however, do not contain hydrogen ions or hydroxide ions. Instead, you would only see those in acids or bases. But we're going to look at a couple of examples. The one you're probably the most familiar with is sodium chloride, or NaCl, which is common table salt. And you'd always write the positive ion or the cation before the anion. And it's very important that the body maintains ionic balance. It's vital for homeostasis or maintaining internal body temperatures or conditions, things like blood sugar and whatnot, no matter what's going on outside the body. So ions are important inside the body and oftentimes called electrolytes because they can conduct electrical currents in a solution or an aqueous environment. Next, let's look at acids and bases. Still looking at inorganic compounds, we haven't switched over to the organic compounds yet. But acids release hydrogen ions and anions. So if you were to take a strong acid and mix it with water, it would release hydrogen ions, oftentimes called protons, plus a negative ion, which is the anion. Here we have hydrochloric acid, and when it dissociates or its two parts come apart, we see the positive bare proton, which is a hydrogen ion, and the anion chloride. Then bases do the opposite. They're going to release a cation plus a hydroxide, or sometimes it's called a hydroxyl ion. And here we have sodium hydroxide as a strong base, and when it dissociates or its two parts separate, we see sodium as the cation and OH negative as the hydroxyl or hydroxide ion. The anions are proton donors, whereas the cations are proton acceptors. So they're able to bind or unbind two protons, generally hydrogen, which is acting as really just a bare proton because it's lost an electron and therefore is a positively charged atom. The way that we measure acid-base concentration is really just using a unit called pH. pH is the measure of the hydrogen ion concentration. And again, that hydrogen ion is essentially a bare proton. An increase in the hydrogen ion concentration, that means we have a pH that is acidic. Low pHs are acidic, anywhere from 0 to 0.6.99 on a scale of 0 to 14 is considered acidic. Whereas a pH of 7 is neutral. And then alkaline solutions are basic solutions, and they would have a much lower concentration of hydrogen ions than our acidic solutions. So a low concentration of hydrogen ions would lead to an increase or higher pH, and anything above 7.01 to 14 in that 0 to 14 pH scale would be considered alkaline or basic. And the pH scale is logarithmic, so that means that something with a pH of 8, for example, would have 10 times more hydrogen ions than something with a pH of 9. So here, if we answer this question, pH measures the concentration of blank ions. Your answer should be hydrogen ions. And if you have a lot of hydrogen ions in a solution compared to another, then the solution with the most hydrogen ions is the most acidic. But if we're looking just at the scale, anything below 7 is acidic, above is going to be basic. Next, we're going to look at buffers, and buffers are really useful in order to maintain a certain pH. Buffers are going to be able to resist abrupt or large swings in pH, so they're just going to basically respond depending on what's being added to a solution. If the pH is rising, so if a base was added to a solution, therefore the pH is going up, becoming alkaline, then you'll see that we'll release hydrogen ions from a component. And the extra hydrogen ions will bring that pH back down. If the pH starts to fall, meaning that the pH is starting to become acidic. Maybe an acid was very abruptly added to a solution. Well, then the buffer can bind to hydrogen ions. It can tie up those excess hydrogen ions, those bare protons, and therefore stabilize the pH. So definitely know the definition of a buffer, that it resists abrupt and large swings in pH. Know that it generally works using weak acids or weak bases that are oftentimes slightly dissociated but not completely. An example is the carbonic acid bicarbonate system, and this is an important buffer system of the blood. We also have a protein buffer system and some other buffer systems in the human body, but we'll talk first about the carbonic acid bicarbonate system, which uses carbonic acid and bicarbonate and essentially the dissociation of one to the other in order to form an equilibrium that is a buffer system. You can see, for example, carbonic acid on the left of the equation at the bottom of the screen. And carbonic acid can break down into a bicarbonate ion and a proton, or what we call a hydrogen ion as well. So if there is a rise in pH, meaning a solution is becoming more alkaline or more basic, carbonic acid can break down into a bicarbonate ion and protons, or a hydrogen ion, and free up hydrogen ions to buffer or stabilize the pH of this solution, keep it from becoming too alkaline. And vice versa, the bicarbonate ions and hydrogen ions, or protons, can combine to form carbonic acid if there was a drop in pH or a solution was becoming too acidic. Again, tying up those excess hydrogen ions would prevent the solution from becoming too acidic, thereby stabilizing, or, for lack of a better phrase, buffering it. So carbonic acid was a weak acid, and so it had an equilibrium with bicarbonate, a weak base, and we saw that we could combine or release hydrogen ions, which are essentially proteins, in order to form that buffer system. Here is just a bigger picture of that equation. Again, you have bicarbonate acid on the left, you have bicarbonate ion and the proton called hydrogen ion on the right, and this would happen numerous times, not just once, but this is an equation in equilibrium, so it can go forward or backwards depending on which you have more of, the reactants or the products. All right, and that is it for the first part of Chapter 2b, looking at biochemistry. Next, we're going to look at organic compounds.